All right, today we are diving deep into the world of polynomials. But wait, forget the boring, dry formulas you might remember from class. I want you to think of this as learning a secret language, a powerful code that lets you build and deconstruct some pretty amazing ideas. You ready? Let's jump in. Take a look at this. Does it look like a secret code to you? I mean, right now, it might just seem like a random jumble of letters, numbers, and symbols. But believe it or not, this expression is trying to tell you something very specific. The only problem is, if you don't know the language, well, it's just gibberish.
Well, guess what? It is a code. And the best part? By the time we're done here, we're not just going to understand it, we are going to crack it. Together. We're going to turn this little mystery into something that makes complete and total sense.
So to crack this thing, we need a new way of thinking about it. Let's just, for a moment, stop seeing algebra as a bunch of boring formulas on a page. Instead, I want you to picture a giant box of Lego bricks. You know, simple, colorful, and just waiting for us to build something cool. Okay, so here's our first official term, a polynomial. The textbook would say it's an expression built from variables, coefficients, and exponents. But in our world, a polynomial is just a finished Lego model. That's it. It might look really complex, but when you get right down to it, it's just a collection of individual bricks all snapped together in a very specific way.
You know, any good Lego builder knows their pieces, right? You've got your flat ones, your 2x4s, the little angled connectors. Well, to understand our mathematical models, we got to do the exact same thing. So let's learn the names of our individual parts.
All right, let's zoom in on a single brick, or what we call a term. Take a look at this, 5x cubed. The number out front, the 5, that's the coefficient. It just tells you how many of that brick you've got. Simple. The letter, the x, that's your variable. It tells you what kind of brick it is. You can think of it as its color, maybe it's a red brick. And that little number up top, the 3, that's the exponent. Think of it like a special feature. Maybe this brick glows in the dark. So, how many, what kind, and any special features. That's all a term is. So once you can spot the individual bricks, you can start naming the things you build, and it's actually super easy. If you just have one single brick, that's a monomial. If you snap two different kinds of bricks together, that's a binomial. And you guessed it, 3 different bricks gives you a trinomial. See, we're really just counting the pieces.
Okay, so we know what our bricks are, we can even name some simple structures. Now comes the really fun part. Let's start building. What happens when we actually start combining these polynomial blocks?
You'll love this. Adding and subtracting is so intuitive. Just think about it. If you had a pile of red Legos and a pile of blue Legos, you wouldn't just mix them all up, would you? Nah, you'd count the red ones and you'd count the blue ones separately. It's the exact same thing in algebra. You only combine the terms that are the same type of brick, the ones with the exact same variable and exponent.
But multiplying? Oh, this is where the real magic happens. This isn't just sorting. This is how you take completely separate piles of bricks and combine them to build something bigger, something new, something way more complex than what you started with. This is where the real building begins.
And you know what? There's really only one simple, powerful rule you need to remember. Imagine you have 2 little Lego kits, and you want to combine them. The rule is this. Every single brick from that first kit has to connect with every single brick from the second kit. That's it. You just have to be systematic, make sure every piece meets every other piece, and you'll create a brand new, amazing model every single time.
So we've gotten pretty good at building things up, but what if we did the opposite? What if we found a really complex, finished Lego model, and we wanted to figure out which original kits were used to build this thing? Well, my friends, that is the art of factoring.
And this slide right here, this says it all. Multiplying is the building process. You go from the small, individual parts to the big, finished product. Factoring is just hitting the rewind button. It's looking at that finished product and working your way backward to find the original building blocks. They're just 2 sides of the very same coin. So the key thing to remember is that factoring is all about discovery. Seriously, it's like being a mathematical archaeologist. You're carefully digging into an expression, dusting it off, trying to find those core components, the original factors that were used to build it in the first place. So where do you even start? Well, the very first step, always, no exceptions, is to look for a common piece. Imagine you're studying a giant Lego model, and you notice that every single part of it, for some reason, uses the same little blue 2x2 brick. The first thing you do is point that out, right? In algebra, that's called finding the greatest common factor, or GCF, and you just pull it right out to the front. Now this is where it gets really cool. Sometimes these math models aren't just random combinations of bricks. Some of them are built using these elegant, well-known blueprints. They're special patterns, and once you learn to spot them, it's like having a key that instantly takes the whole model apart for you. And here are two of the most famous blueprints of all time. The first one, difference of squares, pops up when you have one perfect square being subtracted from another. It always factors out in this really nice, symmetrical way. The other one, the perfect square trinomial, is another super common blueprint. Knowing these is like having a cheat sheet for your factoring. It's a total game changer.
Okay, so let's go all the way back to the beginning. Remember our original mystery? 4x squared minus 9y squared. Does that look a little familiar now? Take a closer look. That's a perfect square minus another perfect square. It is a difference of squares. 4x squared is just 2x squared, and 9y squared is just 3y squared. The code just cracks wide open. It becomes 2x minus 3y times 2x plus 3y. And just like that, we did it. We cracked the code.
So let's just pause for a second and think about what we just did. We learned how to see the individual bricks, the terms. We learned how to snap them together by adding and multiplying. And maybe coolest of all, we learned how to work backward, how to take these complex models apart through factoring. You've basically just become fluent in the grammar of a whole new language. And that really brings me to a final thought for you. We've been treating this like a code or a bunch of building blocks, but what it really is a language. It's a way to write mathematical sentences. So now that you know how to build them and you know how to deconstruct them, the real question is, what new ideas, what new solutions, what new stories are you going to tell?